technology. My supervisor is Branko Šavija and Erik Schlangen. My research topic is Lattice model to simulate the printing process of 3D printed cementitious materials. The presentation can be divided into 4 parts, and I will start by some introduction about 3D printing technology. Over the past decades, we usually use conventional construction method. For this construction method, actually it has lots of disadvantages, like time-consuming, labor-consuming, and low construction speed. However, with the development of the technology, more and more new construction methods came out. 3D printing has been one of the most popular one, and it has lots of advantages, like time-saving, fast construction speed, and security guarantee. What will happen if the cementitious materials meet the 3D printing technology? Here, I will give you an example to show how does it work. We put the cementitious materials into the mixture, then add the water. Due to the hydration process, some hydration product will come out. We transfer the hydration product into the pump. Together with the digital information model designed by the beam or the CAD, we can provide the node coordinate to the nodal. Then, due to the movement of the nodal, we can print the object layer by layer. Here, there are 3 3D objects. The first one from the level of university. Second one is the 3D printed house. Last one is the 3D printed bridge. From these 3 objects, we can see the 3D printing technology has put into the real use for civil engineering. When we print an object, actually we must make sure the materials first can be extruded from the nodal. After extrusion from the nodal, the material should be strong to build the capacity from the subsequently load. So it means there are 2 influence factors. The first one is the buildability. The second one is the printability. We need to find the balance between these 2 factors. Usually we use the experimental method to find the balance, to search for suitable printing time and to search for the suitable administrator. But actually it's too time consuming, and it's impossible for us to try all kinds of materials. So in that way, maybe the numerical method can provide a solution. For numerical method, when it comes to the simulation about 3D printing, actually it's necessary to get the correct failure mode. There are 2 common failure modes in 3D printing technologies. The first one is the plastic collapse. Second one is the elastic buckling. For the plastic collapse, actually the bottom layer in the corner will reach the yield stress, then the whole system eventually failure. For the elastic bucklings, actually not too many parts reach the yield stress, but the global system lost capacity. As I mentioned, my research goal is to do the modeling work of 3D printing. Here we choose Lattice model to do it. The left part is the Lattice models in 3D printing and we can see the different color. It represents the different printing part. When we do the simulation about 3D printing in Lattice model, we usually follow this flow chart. The first, we need to do some model decoration work. It means we need to discrete the models using the Thomson beam. And then we will set mechanical properties. We will set element transient behaviors, including the mechanical property and predetermine the printing time. Then we apply the load into the system, calculate the element stress, then we remove the broken element following the strength criteria and relax the system, continue to the next parts printing. There are 2 potential predetermined failure criteria for the finish of this calculation. If all of the printing part has been printed and without large deformation, the calculation will stop. Or another one, that is if one printing layer can't find the position to print, it means the system will failure, then the calculation will also stop. Here, in the next research, we will use this method and do some simulation to capture the elastic buckling and the plastic collapse. For the plastic collapse, we use the cylinder structure. During the printing process, we can see the deformation will be larger and larger, and especially in this part and this part. Then the system eventually failed, just like it. Yeah, it's really close to the experimental data. It means the lattice model has the capacity to produce the plastic claps. After that, we choose the wall structure to the simulation about the elastic buckling. Then we can, during the printing process, we can see the deformation will be larger and larger. Especially in this part, the displacement out of the plane will happen. Then we review this video again, we can find it. Displacement become larger and the displacement out of this plane will be larger. And this is the final failure mode. And the displacement out of this plane happened. It's called the elastic buckling. We compare with the experimental from our research group. Although we introduced some imperfection in the experiment, but this experiment still produced a very typical failure mode. Yeah, we can see just like it. So it means the lattice model with comparison with the experimental for pneumonia, we can see the lattice model produced the elastic buckling. After this work, next work we can do is do some calibration and validation work to compare with experimental data. In that way, we can prove the lattice model can simulate the 3D simulate the failure mode like the experiment. Review the general procedures. We can see, yeah, we need to follow these steps, and we need to get the input parameters. The input parameters including the mechanical properties and predetermining the printing time. For the mechanical properties, we usually use the calibration through the green strings. The green strings means the early stage mechanical properties, early stage mechanical properties for compression. We calibrate our input parameters. Here we choose Wolf's numerical experimental data, and we calibrate the mechanical property in 0, 15, 30, 60, and 80 minutes. And during this calibration work, we can get the element mechanical properties in the lattice. This part is the calibrated result for mechanical property. If we use these mechanical properties in the lattice model, we can get the macro response just like it. We make a compare with Wolf's experimental data. We found it's close. It's really almost the same. So it means the calibration work is reasonable. Then based on this work, we provide some input parameters to the simulation about the 3D printing and conduct some research. The strength and the stiffness follow the it will change during the printing time. The relationship follows the experimental data. Then this is the printing parameters involves experiment. We use lattice model, we can get the final printing layer is 42, and the maximum radial deformation is almost 10. It's very close to the Wolf's experimental data. The Z position of the maximum radial deformation is 120. It's also close to Wolf's experiment. Only the predicted failure mode, predicted printing layer is larger than Wolf's experiment, but it's close to the Wolf's numerical, I mean the abacus numerical result. So from this part, we can see the lattice model can produce quantitatively predicted corresponding failure mode, but quantitative agreement with the printer experiment should be included. Wolf's research has mentioned the materials anisotropy may be influenced a lot, because in the experiment about the green strings, the specimen undergo a compaction process to achieve the homogeneous, but in the 3D printings, that is not exist. So we need to achieve the heterogeneous in 3D printing simulations. We introduce it just like it. The elastic buckling also follows these equations, and the compression stress will have some materials variations, just like the Gauss distribution. And we introduce it into the lattice model, and we can see, yeah, our predicted printing layer will be lower than before. And it shows a closer agreement to the experimental data, and the maximum radial deformation and the position of the maximum radial deformation almost keep the same with the experimental data. So from this part, we can get the conclusion that is the lattice model can consider the materials anisotropy and introduce the predicted printing layers, produce a closer agreement with the experimental data. From this numerical analysis, we can get several conclusions, just like the conclusion in the slides. And actually, we can see the lattice model can predict the Philian mode and give a closer prediction layers of the Philian mode to the experiment. In the next research, we will take more influence factors, that's like the shrinkage and others, into consideration to improve our model. This is my presentation. Thanks for your attention. Thank you.